Hello. You hear me all right? Cool. All right. So yeah, my name is Daniel. I work for a company called Yelp, and I'm a software engineer on the infrastructure team there. Part of the responsibility of the infrastructure team is to keep the site running fast. So a big part of that is looking at Python profiles, looking for slow pieces of code, and trying to find ways to speed up those slow pieces. So I'm going to share some of the stuff I've learned and kind of part of my process that I go through whenever I want to speed up a piece of code. For those less familiar with profiling, it's basically a tool we use to optimize. So I'm sure many people are familiar with the saying that premature optimization is the root of all evil. This kind of goes along with the rules that the first two steps are don't do it, and the third step is to profile before doing it. So we're going to assume we've done the first two steps and skip ahead to number 3. Identifying a goal. So this is probably good for most processes. I think this is especially true for profiling because you can spend days and days going through a piece of code, profiling, and trying to find speed ups. It's good to kind of have a rough idea of what you want to accomplish ahead of time so that you don't waste a lot of time constantly digging for another few milliseconds. A good way to do that is with the timeit module in Python. So you can run your code using python-m timeit. You tell it the number of repetitions you want and give it a string that it will evaluate. Timeit is smart enough to know that if your code is too fast, it should run it in a loop. So in this case, it runs it 10 times, in a loop 10 times, and it picks out the fastest run, which was 135 milliseconds. For this presentation, I decided to just go digging through my GitHub. I found an old program that's a Sudoku solver, and I thought that it would be ripe for profiling. So that's what I'm going to use for these examples. And I kind of went through as I was writing the slides. Went through like the process I normally would, so it's kind of an organic feel. So there's a couple built-in tools that Python gives us. There's a profile and then a C module version of it called C profile, and these basically wrap all your function calls and time them. And then the output of that is this pstats.stats class. So we can run those. We run them as any other Python module. So we can run C profile, give it a file to output the pstats to, and then an executable Python file. And then we can use pstats and pass it that output file. We tell it to sort by cumulative time and print the top 10 stats. And then we get something like this. So this gives us a bunch of data, the total number of function calls, the number of primitive calls, where primitive calls are calls that are non-recursive. Tells us our sorting, and then it gives us these 5 columns. So number of calls, and then if there's a slash in there, it's raw calls, and then on the right of the slash, primitive calls. Total time is the time spent within the function, not counting functions it calls. Per call, I'm going to ignore because they're basically 0. Cumulative time is the time spent in the function as well as all of the functions it calls. And then of course, the file name, the line number, and the function. So that was a lot of numbers. Let's look at some of the tools that have been created to visualize those pstats. The first is run snake run. It looks something like this. So on the left, we kind of have similar columns to what we'd have in pstats, per call times, total time, cumulative time. On the right is this visualization. So it creates a box for each function call. The size of the box is the representative of the cumulative time, and the empty space in it is the representative of the total time. It's good for kind of getting an overall picture of like what are like the components of the program that you're profiling. I find it's not great for actually digging into individual pieces. This is a relatively small program, and already we see that a lot of these smaller boxes, we can't tell what they actually are, the name disappears. In a large profile, we're going to see that you're not going to be able to read anything. All you can see is like a bunch of lines and boxes. You can click through and dig in, but it doesn't give you a great picture of kind of a segment of the program. At least that's my feeling. I haven't used it a lot. It's also really good at showing you kind of as down the stack time spent in callees, but it's not great at isolating if there's a function that's called all the way down the stack that maybe is called by a lot of different functions. You don't get a clear picture of the total time spent in that function. So let's look at another tool for visualization, and that is gprof2dot. So this thing will take your pstats object and it'll generate a dot format file, and then you can use graphviz.program to generate a PDF or PNG or something like that. And it'll look something like this. So it's a graph. The colors of the nodes tell us relative cumulative time. So red boxes are large majority of the time, kind of the lighter green ones are medium, and then the dark blue are the least amount of time. Along the edges of the graph, it'll tell you percentage of relative time, time relative to the color. Within the boxes, it'll tell you the function name, file name, line number. I don't use this much either. The reason is that, again, on large profiles, you don't get a good sense of kind of within one function call where all the time is going. It becomes very difficult. You kind of have to zoom in, zoom out, scroll back and forth, and it's really hard to isolate kind of one component that you're looking at. But it makes some cool pictures, so sometimes they get used. So let's take a look at pstats. Things broken down into basically 4 calls. Sort stats will allow you to sort by any of the columns we looked at. Print stats to print them out, optionally filter by some calls or a limit. Print callers to print all of the functions that called the function you're looking at, and print callees to print all of the calls within that function. So let's kind of step through the process I would usually take to profile and then optimize a piece of code using that Sudoku solver I mentioned earlier. I always start out just by sorting by cumulative time and then taking a look at the top function calls. So looking at our top 7 calls here, obviously the main module is going to encapsulate all the time. The main run method is going to encapsulate all the time. Stepping backwards, I forgot to mention that this run all basically called solve on 7 different Sudoku boards. So there's a sample of 7. We see that solve here is called 7 times primitive calls and then 11 with recursive. So we know there's some recursion in there to solve it. But I would probably step down to find options for. That's kind of like the first method that's, it's not the high level interface, but it's some implementation. So I would do something like print callees of find options for. Sorry, stepping back a bit. First, I guess I would take a look at the total time and the cumulative time. So we see that cumulative time for find options for is 55 milliseconds, and total time is 27 milliseconds. So we know a lot of the time is spent within the function itself, and not much in functions it calls. So we look at the callees, and yeah, it's kind of evenly distributed amongst the 3 things. We know there's some class in there that's calling equals and hash on. It's not doing all that much. So we can take a look at the code. I tried a few things with this. I tried to remove the assignment and make it a single set operation. Didn't give me much time. I tried moving a few things around. Nothing really got me any kind of improvement. If anything, it got a little bit slower. So I kind of put this aside and decided it wasn't worth spending much more time on it. I was going to move on to the next step. So the next call is find number pairs in cube. So looking at the total time and cumulative time here, we see very little total time. Most of the time is spent in functions this thing calls in the cumulative time. So I again print the callees, and I notice something that kind of stands out here. Show options, 39 milliseconds, that's a large bulk of the time. And I also see that, well, I know that it's going to be calling log.debug somewhere. So take a look at the code, and I see that show options is actually only being called in a debug message. Most of the time, we're probably not actually going to print this out. Log level's probably outworn. So I'm wasting a lot of time generating a debug message, which is not great. I am using the logging syntax that lazily evaluates the string. So we'll never actually fully build this message, but I'm actually calling show options here. So it's wasting the time building up a view of the game board. I thought I would change that to something like this. So now I've moved show options into this board presenter, and whenever this line gets hit, the only operation that happens is assignment to self.board in this board presenter. And as long as my debug level isn't set to, or sorry, my logging level isn't set to debug, it'll never actually call show option. So I've basically saved all of that time. And I think as another small win, it's actually probably improved the structure of my program, because I have a second class now that's only responsibility is presenting the game board, and it's not part of the board class anymore. So I'm going to run time it again and take a look at what that gave me. And it did a pretty good job. It saved me 30 milliseconds on the what was originally 135 milliseconds. So I'm pretty happy with that. But again, I said set a goal, and then I forgot to mention my goal. I think my goal is going to be try to get it under 100 milliseconds. So I still want to do a little more to get this running a bit faster. Going back to the numbers, we noticed that show options is no longer on here, as well as find numbers and cube is also no longer on this top call. So that's a good sign. I'm going to jump down to the next one, identify only possibility. Looking at time and cumulative time again, a lot of time spent in the function itself, cumulative time, small portion of it. So I'll take a look at the code. It's a mess. It's a mess. There's probably a lot of stuff here. I notice there's 2 for loops, one there and one there. So a lot of iteration. There's a lambda expression. And I'm also building up this set in multiple steps. So I might try to rework this, something like this. Oh, and the other thing I noticed that it's possible for this to actually end early. I checked some condition, and I end early if I've matched it. So I try to rearrange it to something like this. So I removed one of the for loops with an iteration generator expression. I removed the lambda with this functools partial operator, which could be faster. And I also changed the thing I'm iterating over in the other for loop into iteration. So if I'm able to fail fast on the self.row or self.call in this get related lists, well, then I might have to actually call get cube, which might save me some time. I tried running time it again, and unfortunately, not much of a gain here. If anything, maybe a little slower. Might leave it this way because it's structured a little better, but definitely have to move on. And the next thing I see is deep copy. So deep copy is built into Python, and you might think, well, it's built into Python, it's probably going to be pretty fast. In my experience, it is a common slowdown that I see deep copy, and I would definitely want to remove it. So in this case, I'm going to, instead of printing the callees, I'm going to print the callers to see what's actually calling deep copy, and I notice that mostly recursive calls, but I do call it in my high-level solve method. I call it 4 times. So it gets called something like this. I've got some pretty standard classes. They do some assignment in their constructor, and I might want to rearrange that to something more like this. So there's now a clone method. The constructors now take options for all the things that it's going to assign to, and that lets me kind of pass in the internal state of the thing I'm trying to clone. I'll run that through time it once again, and I've saved another 12 or 13 milliseconds. So pretty decent, and it gets me under 100 milliseconds. So overall, made a couple changes, saved about 40 milliseconds out of 135. Pretty good for not having to restructure the whole application. So some of the things we saw, and some other common things that I've noticed going through things. Deep copy is always an issue. The documentation mentions that it copies a lot of metadata, so it is a known issue that trying to run deep copy over something is probably going to do a lot of operations that you don't actually need to do. Loops are another common one. For loops tend to be slower than list generators or, list comprehensions or generator comprehensions. So sometimes rearranging a loop to use one of those improves the speed. Within a loop, dynamic variable lookup can actually be relatively slow. So if you get a reference to something outside of the loop and then use that reference instead of doing lookups into globals or lookups on classes, saves you a bit of time. And as we saw in the first example, eager evaluation of things you don't need. So being able to replace things that are with either classes that do lazy evaluation or passing in functions that get lazily evaluated allows you to save some time. There are a few limitations to the standard profiling. Timing accuracy is listed in the documentation. I've never run into a distribution that didn't include a timer with milliseconds or microseconds, but supposedly that is a problem. Threads and processes are a common one. If you have threads in your application, it can throw off your timings because of context switching. It's really only a single threaded profiler, and process is obviously the Python processor. The Python running in one process doesn't have access to all the Python details in another process. Overhead is another common issue because running a profiler add quite a bit of time to the runtime, and then garbage collection can sometimes give you some strange results. You'll notice in a profile where cumulative time and total time don't quite add up properly, and it's because the garbage collector will kind of kick in the middle of something and throw off your timing. So one way to work around at least some of this is to use sampling. So you can create a context manager that will enable and disable the profiler and then dump the results once the context manager exits. And then you can use that in either each thread, or if you've got a web application, maybe one every 1,000 requests or so, you can enable this context manager and get a profile. And then of course you'll end up with a bunch of profiles in different files, so there's built-in support for merging all of those profiles into a single profile once again. So whenever you're doing your profiling, you can get a big picture instead of having to dig through each one and kind of trying to piece it together in your head. And that's basically it. Hopefully I have introduced profiling to some people and made it less, made it sound like a good approach to optimization. That's it. Questions?
You ever ask tell yourself that some people not worth the effort to do some of this optimization?
Usually I will try to avoid it. I won't write a piece of code and go like, oh, okay, I now hate to optimize it. It's usually like, I mentioned for work, if you've got like millions of people hitting some piece of code, that time adds up at the end of the day. So it's usually I'll look at like the significant slowdowns where if I can get like 2, 3, 4% savings across every single web request, that's a lot of extra resources where you can now get 3% extra requests through the existing hardware.
And the other thing is that in general, I kind of usually think of like there's certain areas that tend to be slow, whether it's like high iteration or some sort of file I/O, and those are the kind of areas that I might look at, but rather than sort of detailed code.
Right. Yeah. Obviously, my example didn't have much in the way of file I/O. That's usually why I would try to, like I was mentioning, following the numbers, kind of going through the stack, because if I hit something that's like a database call, well, I'm going to assume that's going to be slower. I might kind of exclude that and try to look for a more obvious thing where, if I find something that's all like CPU bound, then I'm like, well, wait a minute, why is this like formatting of something taking so much time? And I'll dig in there instead of, looking at some kind of I/O.
You ever profile some of your Python and decide your best approach is to rewrite your function in C and then call
I don't think I've quite gone that far. One time I rewrote something in Python, but I have not had to go as far as writing a C module for something in order to get that speed up. Usually I look for some easy wins as far as type of stuff I've been talking about, and then leave it at that. I think a lot of the time your maintenance costs go up quite a bit, and distribution costs and stuff, to having to compile it on each distribution, which I guess Wheel helps with now, but we haven't had that previously.
So you told us, you showed some different tools for visualizing the results. You've only talked about one profiling tool, right, which is the standard library profiling tool?
Right,
so
yes.
Do you know of any others?
There are other profiling tools. I don't know how widely they're used. I think it was Dropbox made one called Plop, which is a different kind of profiling. It's sampling profiling. So every kind of X seconds, it'll just dump all of the function calls on the stack frame, and then it determines the time spent in each by the frequency that a function call will be in that dump. So it doesn't do any kind of timing. I guess the advantage there is that there's less overhead. The disadvantage is you're not as confident in your numbers. It's not actual timing. It's kind of like, based on some statistics, I'm gonna assume that, yeah, if something occurs in the stack frame whenever I interrupt, then it's probably more time is being spent into it. I think there's also one up on Google Code that I haven't worked on. I think it's called Yet Another Python Profiler. I have not used it. I think it's similar to the built-in one and just gives you a few extra bells and whistles.
The reason I ask is that, you mentioned a bunch of limitations.
Mhm.
A lot of the time when there are limitations in the standard library, people are just super fast at coming up with their own versions to overcome those, right?
Right, yeah. I think profiling is probably something that doesn't get done all that often, so there's probably not that many versions of it. I think you're right that the one up on Google Code, the Yappy, is it does talk about threads. I think it has better support for rolling multiple threads.
So gprof to dot.
Yep.
Gprof is the new prof format, right?
Yes, yeah. That's not something that's Python
So
specific.
it's basically working because Python outputs what gprof accepts.
I believe gprof2dot actually has support for that format. It's -f pstats is what allows it to work. So yeah, most of this is pretty standard stuff. I think that works with a lot of different tools. But yeah, there is something built into gprof2dot that supports the pstats format. Cool. I think that's it for questions. Thanks.